Okay, we're still trying to checking for updates. Thank you. Why is the screen this width? I want to check for updates. Why are we in Word? Okay. No, I don't want to go into document one. Why are we in Skype? Good Skype. Wet Word. Well, I'm having the usual computer problems. When you don't have projector problems, you have computer problems. No, I don't want to know about Boingo. I'm trying to get that off my computer. There we go. Okay, we finally got it where we need it. All right. Before we start the usual question of any questions left over, I'm not going to assume that if you don't ask any questions now that you understand everything perfectly. You might be just totally mystified. So where we are, why is that happening? No, I don't want to know anything about Google Drive. They're always trying to kidnap my files off to these cloud things. And, Google does it, and, everybody does it, and your files go here and they go there, and then you don't know where they are. Okay, anyway, enough ranting and raving. I don't know why I have that thing at the bottom there, but okay, anyway. And my keyboard isn't working either. It makes little bonging noises. Okay, there we go. All right, we were in this diagram that's supposed to explain Hardy-Weinberg proportions. And again, bear with me. I think even if you think you totally understand Hardy-Weinberg, maybe you'll see something here that you didn't understand. And I am trying to work out for you, in effect, all possible matings under some restrictive assumptions, which you'll remember include random mating, that the mating is random with respect to this gene, however non-random it may be with respect to all kinds of other things. And equal viabilities, equal fertilities, so everybody gets to reproduce to the same extent no matter what their genotype. Everybody gets to survive to the same extent no matter what their genotype. Equal proportions in the parents that are mating, equal proportions in the two sexes, because if you don't have that, you don't actually get Hardy-Weinberg proportions right away. And nobody migrating in. No mutations, so that a big A times a big A gives you all big A's and not something else. Well, that's entertaining. And most importantly, an effectively infinite population size, which of course you can't achieve in the real world, the universe being finite. And that is needed in order to have the proportions turn out exactly to be what they're expected to be. So if something is expected to occur 20% of the time, well, if we were tossing coins and you tossed a coin, let's say it was supposed to have heads 20% of the time, very biased coin. If you toss it only 100 times, you might not get quite 20% heads. If you toss it 1,000 times, you'd get closer, 10,000 times closer. As you get up to very large numbers, you converge on getting exactly the proportions you expect. So we're going to be in that universe for this calculation. And then, after we get this done, what we'll see is we'll begin to see the role of gene frequencies that gene frequencies are playing. And we can then go on to relaxing some of these assumptions. In this example, there are 50% of the parents who are big A, 20% heterozygotes, 30% little a. Those are actually not Hardy-Weinberg proportions. They're numbers that are easy to work with. Now, I guess the part that I waved my hands at last time, but I don't think I very clearly conveyed what was going on, is why I'm allowed to make this square and have female parents lined up here and male parents lined up down there, and in particular the genes that are in them lined up, and then make boxes here that are products of proportions of those lines. And I could do this. I just thought it would be momentarily helpful to say I could do it in a more complex way. And what I would do then is take the individual genotypes and mark off sections of the square, the top edge for 50% of that for big A's, 20% of that for big A, little a's, and 30% for little a's. And if I did that, and I considered the genes that were coming from those, all of these would all be big A. Half of the genes coming from the 20% will be big A and half little a. I could line them up like this. Let's put the 20% a little further away. I can line them up as a big A, a little a, a big A, a little a, and so on. Or I could also kind of reshuffle those. They're going to be columns of this table. I could reshuffle the columns so all the big A ones are to the left side of that segment and the little a ones to the right side. It wouldn't make any difference in terms of what proportions of offspring you're going to get. Then over here, these are all little a's. And you see this happening in a sort of small sample here. 50% big A. Here the heterozygotes, there's a total of 10 of these, so there's 2 of them that are that way. Here are the little a's giving you all little a gametes. And when you just take the gametes out and line up and you shuffle within the heterozygote category, you can get all the big A's together and all the little a's together. And okay. The other question then is, if we do the same thing over here, we'll get the same result because the males have the same proportions of genotypes. But the other question, why am I allowed to take this marked off 50%, this amount here, and mark it off, and mark off the same down here, and then make a square, and then say the proportion of all offspring that are combine those gametes is the area of the square. Can somebody persuade me that that's a reasonable thing to do, or persuade me that it isn't? Yes, you're very brave. Yeah.
You're looking at the whole population?
Yes. So why are we multiplying these things? Why are the area of this square here is going to be proportional to the distance here and times the distance there? Now, why is that an okay thing to do or not? Yeah.
It represents the mother and father?
Yeah, but suppose I were to say that there's a very non-random mating here, that big A's tend to mate, that big gametes containing big A's tend to get together with gametes containing... Yeah. So what property of this, what assumption that we made pushes us towards this product thing? Maybe I should I should show you a little more here. We're going to end up, this proportion of this line here is 50%, all the ones that came from big A's, and half the ones that came from heterozygotes. 50% plus a half times 20%, that's 60%. And there we are. I've marked off 60% here and 40% there, 60% here and 40% there. Here are these cells in which we're going to figure out what the genotypes are. Yeah.
Is it the assumption that there's no difference in the male and female genotype? That they're all lumped together?
Well, that's part of it, because in saying that this length is equal to that length, we are using the fact that the male and females have the same proportions of genotypes. Yeah.
That just assumes that there's all random mating. There's no difference in viability.
Okay, it is the random mating, but now...
No
if you,
mutation?
Sorry?
No mutations?
Well, there's no mutation. What the no mutation is going to do for us is say that all these gametes that came from a big A were in fact big A, that none of them mutated. Okay. But I know this is kind of showing you something obvious, asking you to tell why it's obvious. And that may be classified as tormenting you, I don't know. But yeah.
We're just going to say that the probability of these two events happening together is, that's why you have to multiply them together?
Right, and you get to multiply when the events are what?
Independent?
Independent. And the way of rationalizing that is to say, well, here are all the offspring that were produced by these gametes. Because everybody gets to reproduce equally, of the total area of this box, 60% of it will be in this column. Okay. Of those, given that you are a big A gamete and you're about to find out who your partner will be in this wonderful new diploid genotype, the fact that you're a big A does not make it more or less likely that the partner is a big A. So of this box, 60% of it will consist of offspring who came with a big A. And those will be big A individuals. And the probability that you get a big A from the mother is not altered at all by whether or not you got a big A from the father. Well, let's see, we started for the mothers up here. The probability to get a big A from the father is not altered at all by the fact that you got a big A from the mother if you're a new diploid individual, a newborn offspring. And when you do that, so we're using the fact of independence, the fact of random mating, which is that the events are independent. And if you shade them in, I think this one may be shaded a little too much. All of these are big A. All of these are little a, and these two are heterozygotes. And there's two different ways of making a heterozygote. One is get your big A from the mother and little a from the father, and the other is the other way around. Those are different. But the resulting, what we're going to assume is the resulting genotypes are indistinguishable. So there they are, and if we say to ourselves, okay, what fraction of all of these offspring are going to be big A's, it is 60% times 60%, where 100% is the total area of the square. 40% times 40%, and here are the numbers for the heterozygotes. Okay, so you do that, and you say, fine, now we have a population of newborns, and they're all going to equally survive, be equally likely to survive. And the result, look just at this column first, is 36% big A, 16% little a, and the heterozygotes are those 24 plus 24 is 48%. Now you'll say, wow, look, we started out with these proportions, 50, 20, 30. Look what we got, it's not the same. You've got different proportions. Something weird is happening. And when the reason is these are not Hardy-Weinberg proportions. These are But now if you say, okay, well, that's fine, but what happens if you do it again? What happens if there is another generation of reproduction? Well, we have to go through this all again. We have to put all the numbers up there and make the boxes. When we do, when we come to mark off this as the fraction of all gametes coming from mothers that have a big A, what will we get? Well, the answer is we'll get 50%, not 50%, 36%, which is the number of big A's, the fraction of big A's, plus half the fraction in the heterozygotes, because heterozygotes segregate half big A's. And if you add those up, 36 plus 24, what do you get? Lo and behold, 60% again. So then you'll say, oh, okay, if these numbers are going to end up being big A's and the big A's and little A's end up being 60-40, do we have to go through all this again? And the answer is no. From this point on down, it's then exactly the same computation. You have 60% and 40%. And what are those magic numbers? Okay, so you're going to get these three numbers about back again the second time, in the second generation. What happens in the third generation? Same thing. Just keeps on going forever. And first of all, you can see there is no tendency here for big A's to go away. There's no tendency for them to take over. They just sit around at the same number as before, and this magic number is the fraction of all gametes coming out of this population of parents. We're seeing it for females here. The calculation is the same for males, given our assumptions. Okay. And as the dramatic sounds are indicating, we're to a very important concept, because what is this? It's the fraction of, if we were a population and made gametes, and then we said, what fraction of all those gametes contain big A's? That is what's called the gene frequency. It's not a great name, because the issue, what do you mean, the gene? I mean, which are we talking about? The word gene in genetics is actually somewhat ambiguous. If I say, we've got, let's say we look at our hemoglobin beta loci. So we're a bunch of individuals that we have diploid genotypes that are hemoglobin beta locus. Somebody could say, what's the gene? Answer, hemoglobin beta. Okay. Well, there might be two alleles. We could have a big A or a little a, let's say, or hemoglobin beta. You might have regular, normal hemoglobin beta and sickle cell. But there's a lot of other variations you could have too. If you look at two of those alleles, you could say that there's a big A gene and there's a little a gene. Well, now the word gene means something different. It's not talking about the locus, it's talking about the particular allele. Or you could say, I have in me two copies at that locus. In other words, I'm diploid, I've got two genes. Wait a second, the word gene now means an individual copy, whether or not it's identical to the other one, they count them as two. The word gene is a little fuzzy that way, it gets thrown around. So here, the gene frequency is referring really to the frequency of alleles. It would have been better from the beginning to call it the allele frequency, but unfortunately, although people will understand it if you say it, it's not the usual term. So these things we'll call gene frequencies, and they are in some sense there all the time among these parents. In the gametes they produce, the proportion of big A's and little A's was 60%. And it would be the same thing if you said, well, let's just go into the parent. Let's not worry about what gametes they produce. Let's go into the parent, count up the copies of the gene, and ask what fraction of them are big A. And the answer is, that's 60% also. So you can think of it as either what's in the gametes or how many copies are in the parents, because the essence of Mendelian reproduction is that you get a random sample for each individual of its two copies, and thus if all these other assumptions are holding in the gametes coming out, there is just a random sample of the copies in the parents. So you can think of it as either of those. Okay. If you do, here comes the math. I try to reduce the number of equations as much as possible in the course. I have had people complain that you drown us in equations. I think one year I counted the number of equations because I was so upset about being accused of drowning, and I think I came up with 12. But anyway, having seen this picture, you can do it all more generally. You can say a fraction capital P, or big A, a fraction capital Q, and a fraction capital R. These, by the way, are called genotype frequencies. What's this? Well, it's this one plus half of that, P, capital P plus a half of capital Q. This is a half of capital Q plus R. And those are the gene frequencies, little p and little q. And when you make the boxes, you find that the fraction of the whole area here, that's big A's, is little p squared, little q squared for the other homozygote, the heterozygote twice pq. Now when you take these and you say p squared plus half of this, what is it? It will come out p. That may not be obvious. Okay, here we go with higher mathematics. This is high school algebra. Some of you might have been taught it before high school. If we have p and q where they add up to 1, this is the important mathematical principle that the total frequency of everything is 1. Something that students often forget when they do problems. They end up turning out proportions that don't add up to 1. Okay. Then, if you take p squared plus a half of 2pq, what will you get? Well, the half and the 2 cancel. So you get p squared plus pq. So maybe I'll make it cancel there. And you look at that, and then you do the other sophisticated mathematical technique, which is factorization, something you were taught in high school. You look and you go, p doing something and a p doing something. It's got a p in every term. Let's take a p out front. Then what are we multiplying? P plus q. Then, using the principle that the total frequency of everything is 1, that's p times 1. So this is always going to turn out to be the gene frequency. So will that. What happens in the next generation? You just go back around, you still have P and Q. So the genotype frequency started out maybe different. Capital P, capital Q, capital R. Not necessarily the same as these. It was not the same in our example. But there was a gene frequency there. The gene frequency, when they get together at random, the random union of gametes being equivalent to random mating under our fairness assumptions, when they get together, you get these proportions that show up just from combining things at random. And so what you have, and when you work out the gene frequencies in them, well, if you think about it, it's just a pair sample of genes coming from the females, a pair sample coming from the males. The resulting gametes are going to have, if you total up all their genes, they're going to have the same gene frequency. And that gene frequency continues to hold and continues to give you Hardy-Weinberg proportions every generation. So Hardy and Weinberg in 1908 independently found this. And one of the things that they found is you have these magic proportions. They're just random combination proportions. But you also, more importantly, have the principle that those proportions really came not from the details of the genotypes, but from the proportions of big A and little a genes, the gene frequencies. And those gene frequencies in this calculation aren't changing generation by generation. Through the whole thing, they remain the same. Okay, so you have Hardy-Weinberg proportions, and this, of course, refutes Fleming Jenkin, who was working with a blending theory where when big A's and little a's get together, he was implicitly assuming that you get out middle-sized A's. Actually, he, of course, didn't know anything about diploidy or genotypes, because nobody did, except for Gregor Mendel at that time. He was writing, Jenkin was writing 3 years after Mendel published his paper, but of course he had never seen it and he would not have understood it. So some people, by the way, there was a moment in the 1850s when Gregor Mendel actually traveled to England. He was in 1851 there was a great industrial exposition in London that's very famous, where basically Britain showed off its industrial prowess to the world in the great Crystal Palace, I think it was the Crystal Palace Exposition. And people traveled from all over Europe to see this wonder, and one was a delegation from Brno, formed with Gregor Mendel in it, and they traveled on the relatively new railroad trains across Europe, steamer across the Channel. I've done that. It is, you no longer have to do it, but I've done it, and you don't want to do it because the English Channel narrows down and the waves get higher. And seasickness. And they got to London and they saw the expedition, had a good time, went back to Brno. People said, if only Mendel had gone to talk to Darwin, we would have been way ahead. And I think that's somewhat silly for two reasons. One, I don't think Mendel spoke English. A, and B, if he had, who would he have been? Darwin might have been nice enough to have him, to allow him to talk to him, because Darwin was pretty good about that. But here would be this obscure, incomprehensible monk from teaching brother from Brno, and he had some obscure scheme of genetics that he claimed to have found working with peas. And there is no reason to believe that Darwin would think that this was a general property, that this was a great thing. It's just some obscure ratios that this guy from Brno found. Well, we'll have to think about it. In fact, it's been found that in Darwin's library, there was a copy of one of the journals that Mendel's paper was in. So Darwin could have read it if he bothered to read German. But in those days, I don't know if you've seen very old signature sewn bound things. Things are bound in signatures, and you have to take a paper cutter and cut the folded edge of the signature. And Darwin's copy of that journal, all the signatures weren't cut. Darwin had never opened it. So, even if he had, I don't think he would have been revolutionized. I don't think he would have just said, well, this is interesting, but other people might come up with different results. Besides, that guy's accent was so weird I couldn't understand him half the time. You know, that kind of thing. Okay, so you get Hardy-Weinberg proportions. When you go to do it in some examples, I just want to show you calculation of gene frequencies. Suppose you sample a population, you get 200 individuals, and here are the numbers you get of each of these three genotypes. How do we do it? Well, we can do it as we did in the projection. Here are the numbers. You simply take, you get the frequencies, the genotype frequencies, by dividing by their sum, which is 200. And you'll get 41.5%, 31%, and 27.5%. And then you say, okay, we're going to imagine that we're producing gametes. All the gametes coming from here are big A, and half the gametes from the 31%. That makes 57%. Okay, that's one way of calculating the gene frequencies. The other way, same data, is just to count copies of the genes. And we'll get you the same answer. So here, the 83 big A's have a total of 166 copies of big A, because each has 2. And no little a's. For little a, 55 gives you 110 little a's and no big A's. The 62 heterozygotes give you 62 of each. You take those numbers of copies, tote them up, you get a total of 228. copies of big A and 172 copies out of 400. And when you take those fractions, they are the same as you got on the previous, which is comforting, 57% and 43%. So that's the two ways you can think of calculating gene frequencies, is counting copies. If we are a population, you could count how many copies there are in us, or you could have us contribute gametes into some gamete pool and count what fraction of the gametes. And by Mendelian reproduction, those are the same. Okay. Now what we want to do is go from there to start relaxing the assumptions. And what we're going to do is say, okay, you've been saying that you haven't been saying that everyone survives, but you have been saying that survival has nothing to do with your genotype. You haven't been saying that everyone reproduces, but you've been saying that the probability of your reproducing doesn't have anything to do with this particular genotype. It might have something to do with another gene, with another locus. Okay, so what I want to do is think of a case where the probabilities of survival, here we'll make them viabilities, probability of survival to adulthood.'s say that big A's always survive to adulthood, but little a, and heterozygotes also, but little a only survive 70% of the time. So we're going to have viabilities that are these. Now, in the notes, this is, in the PDF of notes for this lecture, I have a rather extensive argument about the concept of relative fitness and absolute fitness. And in this case, what it's going to be is that here I'm saying, we could say, well, everybody survives. But suppose I said, actually, this population is, suppose I were doing the same calculation that I'm going to do, but now you're in a situation where not everybody is surviving because the population has overrun its resources. There's rather too little food around. Maybe these numbers would change. They're going to drop. The probability of survival is going to go down because you're not having enough food and so on. But if I make one little assumption, you'll find out that it doesn't affect things because I have these as 1 to 1 to 0.7, but suppose we're now in a situation where the probability of surviving by getting enough food is the same for everybody. And suppose it's 1/2. Suppose it happened to be 1/2. This number then drops to 1/2. That number drops to 1/2. And what happens here? We're running out of battery here. What would happen to that number? If it were the case that you're starving, you're surviving the lack of food, is completely independent of what your genotype is. Well, I claim that of the 70% that would have survived, then half of them would survive. So now the numbers, instead of being 1 to 1 to 0.7, become 0.5 to 0.5 to 0.35. But their ratios haven't changed. Their ratios haven't changed because the probability of survival wasn't really dependent on the genotype. So when I use these numbers up here, I'm going to say it's not that those are the absolute probabilities of survival. Those are the relative probabilities relative to somebody, and we could take big A, for example, as our standard and say, relative to big A, your probability of survival is what? Well, it's the same, and it's 0.7 at that. I may be totally confusing people here, but there is a distinction between absolute fitnesses, which is what you would actually see if you watched the life cycle, and the relative probabilities of survival. And what I'm going to be dealing with is the relative probabilities. And that's going to be because in the end we're going to take ratios of things, and those probabilities of survival due to surviving the shortage of resources are going to cancel out of the whole thing. I have a big discussion of that in the notes, and if you want to look this up, check out there, and I think it'll become a little more plausible than I can do just sort of waving hands. So suppose we start with relative fitnesses of 1 and 1 and 0.7. And we start with an initial gene frequency of 0.2 for big A. So now what will the Hardy-Weinberg proportions be at the beginning of the generation of the newborns? Well, 0.2 squared, that's 0.04. The other allele is what? This is 0.2. What's little a's gene frequency?
0.8.
Yeah, 0.8. 0.8 squared is 0.64. Twice their product is 0.32. So they're the Hardy-Weinberg proportions. And now we're going to say, let's just treat these as probabilities of survival. And let's ask, of all these newborns, what fraction are surviving big A, surviving big A, little a's, and surviving heterozygotes? And the answer is going to be the product, 0.04, 0.32, and 0.448. The catch is, those are not the proportions of the resulting survivors. Those are the proportions of the original population that are surviving ones of each genotype. But there's also some that died, namely 30% of the little a's. So if you add up these numbers, you'll see that 0.808 of everybody survived on average. Now, if you want to know among the survivors what are the proportions of these genotypes, you have to divide by that. So if we divide by the total, 0.0495, 0.396, and 0.554, of course rounded them off a little. So now, as a result of these differential viabilities, the proportions of the genotypes went from the Hardy-Weinberg proportions to something else. And you might say, okay, are those going to, what happens if those go out and reproduce? Okay. Well, you get the same formation of a box, and once again you figure out the gene frequencies, and now there's a little bit of a difference. 0.0495 of everybody are surviving big A. Half of the heterozygotes are surviving and giving a big A. Total, the gene frequency is 0.2475. Now remember, we started out, the gene frequency was 0.2. Now it has changed. It's 0.2475. So all this is just, just tabulating things, basically. For the little a, if you do the same thing for little a, you get 0.7525. Those numbers add up to 1. And now you can say we had newborns in these proportions. We had differential viabilities. And now we have genotype frequencies. If you go out and you make up the square and you do random mating among those survivors, you get more Hardy-Weinberg proportions, but now they're different. It's 0.2475 squared. That's this number. Twice their product, and 0.7525 squared. So with the assumption removed that all individuals survive equally, the gene frequencies change, and correspondingly the Hardy-Weinberg proportions change. And that, if you keep it up with 1 to 1 to 0.7, if those are also the viabilities in the next generation, you can go back through this repeatedly, and you'll keep changing the gene frequencies, and the Hardy-Weinberg proportions will keep shifting. Now, you often hear about Hardy-Weinberg calculations that it's a Hardy-Weinberg equilibrium, and that can be very misleading. there's no tendency for the genotype frequencies to go back to 0.2, the gene frequencies to go back to 0.2, or the genotype frequencies to go back to these. They're only in equilibrium in a very limited sense of if you manage to change the genotype frequencies without changing the gene frequencies, then you'll get back out the same Hardy-Weinberg proportion. But if you change them in a way that does change the gene frequencies, it won't go back to its original gene frequency or genotype frequencies. And that's what's happening here because we're systematically discriminating against little a's. They're getting killed off. The point I wanted to make about relative fitnesses, that you can take the fitnesses and just scale them so that some particular one of them is 1, let's say big A, big A. And then you've got what you might think of as relative fitnesses there. You're giving the ratios that they're in. The point there is made that if I were to take each of these numbers and change it owing to ecological problems, I say I drop this to 10%, that to 10%, and this to 0.7. In other words, I'm dropping them by 90%. I still have the same ratios of the viabilities. When I go through this calculation, when I come here and divide by the total, I will in fact get the same numbers, provided that this ecological problem is evenly distributed among the genotypes, that everybody faces the same difficulty getting resources. Or if I go, suddenly the population finds itself with unlimited resources, it still has this problem that the little a's aren't as able to survive, but for terms of food, now there's lots of food, well, you might multiply all these numbers by 3. But once again, when you went through the calculation and came to dividing by this thing, which would now be 3 times as large, you get the same proportions out. So it's the relative fitnesses that matter, not the absolute fitnesses, under this assumption that whatever happens to density-dependent population size growth, as long as it falls equally on the genotypes, independently of whatever other fitness problems they have, you're okay. In a sense, that issue, as I mentioned in the printed notes, means that if we can just work with the relative fitnesses, we got rid of ecology. We're now talking about the genetic composition of the populations, and whether those populations are at high density or low density won't matter. We can make a nice, neat divide and push the ecology off that way and say we're going to work with the population genetics. I think I'm ranting and raving, so I should go on. Okay. If you do this with algebra, it's just the same. It just starts with, let's say you start with Hardy-Weinberg proportions at a gene frequency T. You have relative fitnesses that are these numbers. They're now just symbols. W with the subscript of the genotype. What fraction of everybody up here are in the category surviving big A, surviving heterozygote, surviving little a. It's just the products of those. P squared times W big A. In other words, there were P squared of these, and a fraction W big A of those are still there after selection. Their sum is not necessarily 1 anymore, but if you divide through by it, you get the genotype frequencies. And I'm just showing them as this thing over sum, because in a moment I'll persuade you that you don't really need to know what that sum is. And now if you say, and here I've left out a step here, so I'll try to do it on the blackboard. Get my eraser. If you have the 3 genotypes, I like to say to people that In this class, you will learn about the population genetics of big A and little a. If you want to know about big B and little b, you've got to take another course. You'll be seeing these again and again. The fraction of individuals surviving that are big A is p squared times this w thing divided by the sum of all three of these numbers, of these numbers. And I'll just put that as sum. And then here, twice PQ, the fitness over sum. And similarly, although we won't use that right away. And now you'll say, okay, we want to figure out what the gene frequency is. What is it? It's this plus half of that. Okay. What's the half going to do? It's going to cancel the 2 out. So you'll get p squared w big A, and 1/2 of 2pq, that's pq w of the heterozygote, all divided by the sum. And I'm just going to do those two, and then say, now add those up. Well, if you want to add them up, they're both over the same denominator. So here it is, right here. It's p squared w big A plus pqw heterozygote over the sum. And what is that sum? It's just that. So there's the formula. There's the general formula that says, if I start with the value p, and q is just another name for 1 minus p. If I start with a frequency p, what will I get in the next generation? Well, you evaluate this formula, which is a couple of quadratic-y kinds of things over each other. But all it is a simple bookkeeping. There's no mystery here. And you'd say, well, I could make a computer program which I fed in the numbers w big A, all the w's, and I fed in a value p, and I made sure that q was 1 minus p. And then I just evaluated this. You get the gene frequency in the next generation. And you could put it in a computer and crank it and work out the gene frequencies in each successive generation just by cranking through that formula. Here's the there's one last thing. I'll just mention it, and I'll start with that next time. You can also do a little simplification. The denominator we're leaving alone, but the numerator, we see everybody has got a p in it, and if you work with the algebra of population genetics, you should sort of have this overwhelming desire to factor out the p. When you do that, and it's p times this strange quantity, which is p times w big A plus q times w big A little a. Okay. Now, if we interpret those, there's an interesting interpretation. This is the gene frequency. The denominator is the average frequency of everybody. Sorry, the average fitness of everybody. If each of you were a genotype and each of you knew your fitness value, and I asked you for those fitness values and then averaged them, p squared of you would say it was this number, 2pq of you would say it was that number, and q squared would say that number. And so that's the weighted average of the weighted by the frequencies of the genotypes among you. And I'll just mention what this is and let you get out of here. What this thing is the average fitness of genotypes that carry big A's. So if I went and picked up individual copies of genes from you, and at this locus, and I said, are you a big A? And you say, no, I'm a little a, the gene you got picked up. And you say, I don't want to, and I'd say, I don't want to know about you then. Are you a big A? Yes. Okay, what's the fitness of the individual you're in? The average fitness of individuals that big A's are in is this thing. So this is a very simple formula. It says P times the ratio between the mean fitness of big A bearing individuals over the mean fitness of